Swayam Prabha. Digital India. Educated India.
The network flow problem is something that has extensive practical application, right? So many practical problems in operations research can be posed as network flow problems, and in the area of design and analysis of algorithms, it shows up nearly in every place as a subroutine. Right? You make a function call to solve a network flow problem when you're trying to design algorithms, right, and understand their asymptotic complexity. Okay. So what we will do is we will introduce the problem. So we'll introduce the network flow problem, right, and we'll define. We will try to work with a running example, and we'll prove a main result, right, which is called the max flow min cut theorem. And if time permits, complete the proof of a few small lemmas. So this is basically the plan, right? So as far as the definition of a network flow goes, so what we need is a directed graph D V comma E, and there is a capacity function, right, which is for every pair of vertices, right. For the purposes of this discussion, let us assume these are positive integers, right. So, or rather non-negative integers, right. And if C of u comma v takes a value 0, implies that E is uv is not in the graph. So that's kind of a convention that you can keep in mind, right? And we'll also make one more assumption on the diagram, that there are, in the given graph, there are no parallel arcs. In other words, there are no arcs which look like this. Right? The given graph T. We will create some intermediate graphs in which this property will not be enforced. Right? We will keep that also in mind. Right? And I will draw your attention where in our mathematical analysis we use this particular property. That this is called an anti-parallel edge. Right? So A to B an edge and B to A an edge. This is not there in the given graph. Right? Okay. So what is the question? The question is about an object called a flow. Right? So when you think of a flow, you can think of something that looks like a current, right, in a resistive network. Fine. So in particular, by the way, I also forgot, the input also consists of a pair of vertices called S and T, source and terminus. Right? So now I am going to define this object which is called an ST flow, right, source to terminus flow. It is a function f from V cross V, right. And again, to keep everything simple here, we will assume that this is non-negative integers. Fine. What are the properties that this f is going to satisfy? It is going to satisfy that the value of f of u comma v is upper bounded by the capacity of u comma v. This is the first condition. The second condition is what is called a conservation condition, which says that so it's called a conservation condition. It's like your Kirchhoff's current law, right? For every u belonging to V minus S comma T, except at the source and the terminus, right? If you think of your school circuits which consist of resistances and a voltage source, except at the voltage source, the positive and the negative terminus of the voltage source, at every other intermediate point, whatever current comes in has to go out. That's a conservation condition. Fine. So that's exactly what is stated here. Right. Any such function, right, is called a flow. Right. It's called an ST flow. Except at S and T, this conservation must be satisfied. The value of the flow cannot exceed the capacity, and it cannot be negative. Fine. So let's do a small example, right? And maybe before I do the example, I can even tell you what is the value of a flow. The value of the flow is calculated at S, right? It is a very, very important parameter, right? So in other words, if you look at S and you look at the edges which are oriented out of S and you look at the edges which are oriented into S, the value of a flow is the sum of the flow on these edges, right, and the sum of the flow on these edges is subtracted, or the value f on these edges is subtracted from this. That's what this term basically says. Fine. Right. Right. So let's observe one small property before we go to the example. Observe that the function which assigns the flow value 0 to every edge, right, is indeed a valid flow as per the definitions. Right? It's less than or equal to the capacity, it's greater than or equal to 0, and conservation is very obviously satisfied. So f assigning 0 to every pair of vertices is indeed a valid flow. Therefore, the value of that flow is also equal to 0. Therefore, the value of this flow is at least 0. It's a positive number. It's a very important thing. So we are interested in a couple of questions, and we will try to answer them during this lecture. Is it bounded? Meaning that, is it possible that for a flow network, the value of f is infinity? Right? And the third question, how do we find it? Compute it, and secondly we will be interested in how to compute it efficiently. So now let's do an example, right? So this example is taken out of the textbook by Corman, Lyserson, Rivest and Stein, the 3rd edition. So it's exactly the same example that I have. So this is the flow network that we will try to keep as a running example. So what you see, right, are the nodes and the edges. The edges are oriented. Every edge has a capacity, right, and you will notice that this edge and this edge, there is this intermediate vertex. So in a sense, it is a way of ensuring that if you have parallel arcs in your given flow network, anti-parallel arcs in your given flow network, you can kind of cheat and just draw it in this fashion by keeping the same capacity. Right? That's a way of dealing with anti-parallel edges, right, that may already occur in your network. You can eliminate them by adding an additional vertex in between them. That's a small technical point. So let's do a small exercise. Let's compute a non-trivial flow. So can somebody come up with a non-trivial flow here? Non-trivial meaning that not all 0. So in other words, you must, let me also name the vertices, right? So A, B, C, D and E. So in other words, you have to give me values for all these pairs, right? So there are 5 2s are 7, 5 plus 2 7, there are 49 pairs, right? You must give me values for f of u comma v. It must satisfy those conditions of a flow. So can somebody give me values for f? So it's quite an easy exercise just to give me a flow, right? So you just have to ensure that the value doesn't violate the capacity, it is positive, and you should ensure that it satisfies the conservation conditions. So any answers? Yeah, just give me the value of the flow, we'll just check. I have not stated any of these things. I only said, so that's a good question, right? So what she is asking is that, is there a constraint that whatever starts as S should sink at T, right? So I have avoided stating the definition of a flow in that way, but you will see that every flow has a current like behavior. It will start at S and it will sink at T by these definitions because of the conservation condition. So the conservation condition says that except at S and T, the value of the flow must be conserved, which means any flow that comes into S, so to speak, that is what this condition says, any flow that comes into a vertex u, right, should also leave that vertex u, right? But at S and T, there is no such condition, right? So the natural thought process is, if you think of this function flow f as a liquid or like current which is flowing through a network, right, where will it go if it starts from S? We will formally prove that if it starts at S, it will indeed reach T. Right? It's only an informal way of speaking when you say that everything that starts at S will go to T. The mathematics will actually show it to you in a slightly different way by showing that conservation is respected. Right? We will do that formally, and I will remember to draw your attention to it when we come to that step. But I have not placed any such constraint explicitly. So can somebody give me a flow stream? For each arc, I will give a flow of, okay. Will that satisfy all the conservation conditions? So a natural way to think about it, I am sure many of you are thinking about it, is to avoid this complexity, right? So what is the difficulty that he has created? He is trying to basically give a flow to, a non-zero flow to every arc. But I ask you to give a non-zero flow, which means that it is okay if you give non-zero flow to some arcs, right? So the natural thing to do is take a path from S to T, right? Take the cheapest weight path on that cheapest capacity or the least capacity edge on that particular path, right? So this is ST. Imagine this path SAB, right? Now you define the flow as follows: f of s comma a is equal to f of a comma b is equal to f of b comma t, which is 13, because you cannot violate the capacity on the other edges. So I give the flow value to be exactly this. Fine, right? So now let us see if all the conditions of the flow are everywhere else it is 0. For every other pair it is equal to 0. Now let us check. Positivity is obvious the way I have defined it, right? It's also clear that the capacity of no arc is violated. The flow value given to every arc is lesser than or equal to the capacity of that arc. It's only the conservation that you should worry about, and you should remember that we are worried about conservation only at vertices other than S and T. So you look at A, right? The edge that comes in from S to A has been allocated a flow of 13. The edge going from A to B has been allocated a flow of 13. So it is conserved at A. The same is conserved at B. Fine. So therefore, we have a non-trivial flow. What is the value of this flow? The value of this flow is 13. You just have to apply the formula. You count the flow on the edges which are going out and subtract the flow on the edges which are coming into S. There are no edges coming into S, all the edges are going out. So therefore, the value of the flow is 13. Fine. Okay. Can you increase the value? I want a larger flow, and in which case you will modify the flow now. So let us now do this, right? So SD, right, is equal to f of dc is equal to f of ct, and what would it be? 4, right? Fine. So therefore you have taken this path, and therefore this is another plus 4 now, right? Can you increase it further? SDC BT, right? That's right, right? What would be the flow that you would give there? 7, right? Fine, right? So therefore it looks like I can add, but now you have to update the flow of f of s comma d is going to be 4 plus 7. It is going to modify, right? That's going to be 11, and f of d comma c, what is that going to become? That's also going to be 11, right? Right? And then that 11 is going to split into 2 parts, right? That is f of c comma b is 7, and f of c comma t is going to be 4, right? What is f of b comma t? 13 plus 7, it's going to become a 20, right? Fine. So this flow that I have written here and this flow that I have written here are different, though I have used the same name, right? Now this, the flow below, right? That's going to become plus a 7, right? So it's 24. Can you increase this further? Right? Why can't you increase it? So the intuition is that you probably have hit some kind of a limit now, because the amount of flow, right, going out of S is 24 units, right? And you see that there are these two edges whose capacity total is 24, right? So intuitively we will formalize this in the proofs that we do. You cannot probably cross 24, and we have achieved the maximum. Fine. This is the theory that we are going to build and prove. So the first step is to formalize this whole procedure that we did. Iteratively we found, right, a flow, right, one after the other, and kept adding it to the flow that we have computed, right? In this example it was very easy, right? But there are examples that you can come up with where you can have a lot of lot of mysterious behavior, right? To avoid them, it's important to follow the template as I am going to present now, and this template is called the Ford-Fulkerson template. So first I will present the template, and then we will do all the necessary formalization for arguing the correctness of this template. The first step, the template starts with f is identically 0. If there is any doubt with my notation, please ask me, because this must be very new to most of you, right? I mean, but unlikely that you have studied this. Right? Then what do you do? You compute a graph called GF, right? So I will also put a marker here, right, which is, this step is called repeat, right? Or rather, let me remove this, let me call it loop. Right? You compute GF on the directed graph G for S comma T with capacities C. I will define what GF is, and GF is called the residual network. Intuitively, you can imagine the residual network is a network that somehow encodes information about how much more capacity is available on all the arcs. It's a very loose way of speaking. I will formalize a residual network shortly. Find the ST path in GF, right? Consider, let me call this path P. Consider Cp the residual capacity, this also I will define, the residual capacity of P. Right? This is what we did. You took a path and you decided how much flow you could assign to the edges on that particular path, right, without violating the capacity. This capacity will be formally defined as a residual capacity. Right? Then using the edges of P, right, this flow is called f prime, such that the value of f prime will be equal to, well, right, f prime, and consider a new flow which we will denote as f augmented with f prime. We will consider a new flow which is called f augmented with f prime. Right? Now let me, in the reverse order, define the values of these flow of these parameters. Right? So f augmented with f prime of u comma v will be equal to f of u comma v, which is a flow, right, that you started out with at the beginning of the loop, plus minus f prime of v comma u. And we will prove properties of this f augmented with f prime. This flow we will prove some interesting properties, and we will repeat this step till you can't find an ST path. Find an ST path. Okay, just one intermediate step. assign to f, f augmented with f prime before you continue the loop. Output f. So this is the Ford Fulkerson template. Right. Let's just review this. You start with a flow equal to 0, then you start a loop. Right. At the beginning of the loop, you compute a network which is called a residual network. Right. So in this residual network, you will have modified capacities depending upon the current flow that you have calculated, which is f. Right. This residual network will encode how much capacity is left on each of the arcs and some very important additional information. Then it will try to find an ST path. If there is no path, it will exit the loop and print out the flow that you have calculated so far. If it finds a path from S to T, it will calculate a flow f prime, right, using the capacity on that particular path. Fine. And then it will augment the flow f with this f prime as given by this formula. Right. So for every u comma v, you take the flow f of u comma v, add f prime and subtract out f prime of v comma u for every edge. This will be considered as the new flow function, right, and that will be stored inside f and the loop will continue. Fine. So we are going to analyze this by defining each of these important parameters here and proving interesting properties of it. So let us just define f prime clearly now. Right. F prime for an ST path. It's exactly what we did, so you just have to commit it to memory. Right. So f prime of u comma v is equal to the minimum over all edges belonging to path P. Okay. So let me say E is of the form xy, okay, capacity of xy. So when I mean edge belonging to the path, in the direction of the path. So if the path looks like this, S, A, B, C, then for every edge on the path, f prime of u comma v is going to be the minimum capacity of the edges which are on the path in the direction from S to T. In the direction from S to T. Fine. Okay. F prime for everything else is going to be equal to 0. Recall the way the augmentation happens per edges. You take the old flow that was in f, add the new flow and subtract the flow which might have come in the opposite direction. So let me show that to you pictorially. Right. So let us assume that the edge u comma v had a flow f of u comma v, right, earlier. F prime, right, gives it a flow, right, f prime of u comma v, but for some reason f prime also gives it a flow, right, f prime of v comma u. Right. It could also be 0, right, some of these terms could also be 0, so you don't have to really worry about it, right. So in this case, f augmented with f prime of u comma v, this is a short form for this long formula, f of u comma v plus f prime of u comma v, that is the flow in the direction u to v, and subtract out the flow in the opposite direction, very much like current calculations that you might have done when you did current calculations in resistive networks, right. So it's just the same. Just keep this in mind. So now what do we need to define? We need to define where do we pick this ST path from. Right. In the example that we did, it was very easy, right, but there can be more complicated situations. So let us just define the residual network. So the residual network for a given flow in a network G. So you are given the initial flow network G, remember, without any parallel arcs and so on, without anti-parallel arcs, right, and you have a flow F, we are going to compute this residual network which is called GF. The change is very simple, it just keeps track of residual capacities. Let us just see what the residual capacities are. C, the residual capacity in the network for the flow F for u comma v is equal to C of u comma v minus F of u comma v. If uv belongs to the H set of G. Fine. So what do? You just say that, okay, the flow F assigns to uv a certain value. How much residual capacity is left? Whatever was the original capacity, subtract it out from here for the edge which is in the network. It is equal to f of v comma u if Vu belongs to E. This is a bit of the tricky one, right? Remember that in the network you don't have anti-parallel edges, so which means you don't have this. Right? This you don't have in the given network. So actually it only looks like this. So if you allocate a flow value of 5 to this arc, then the residual capacity of this arc is its capacity minus 5. But you also keep track by adding this arc and giving it a capacity of 5. In the residual network, this anti-parallel condition is violated. It stores some very important information. The important information it stores is that how much of flow you have given to u comma v, the capacity of v comma u is given to be that. Right? So this is well defined. It is 0 otherwise. So instead of running this residual network on the example that we did, so what I am going to do is, right, so you can attempt that by yourself. I am going to now prove something very interesting. I'll come to this proof a little later, but I'll convince you of this, move ahead and prove a sequence of properties, and we'll come back to this. If F is a flow in G and F prime is a flow in GF, then F augmented by F prime is a flow in G and so this is the measure of progress that we are going to see, that the Ford-Fulkerson template, right, will in some sense, superficially speaking, keep improving the flow. By the way, is a flow in G and its value is the value of F plus the value of F prime. Right? Pictorially, what is the thing that you should think of? You had this flow network, you are pushing a certain amount of current out of S, right? Then you calculated the residual network. Then you are able to push a certain amount of current out of S inside the residual network. Right? If you carefully add up the currents, now you can't blindly add the currents, you might have to subtract certain things also. Right? That is why it is not just written as addition of the values. I have written this more carefully. We will show that you can, whatever currents you add is the total current that goes out of S. Right? So that requires some amount of careful analysis, because if you look at the value of the flow, there is an addition term in S at S and a subtraction term from S. Right? We should still ensure that this addition is indeed correct. That is what we are going to prove. Fine. Let's assume this for now. I will come to this in a minute. At the last 15 minutes of the lecture, I will write a proof for this. It's fairly easy and algebraic and pictorial also. It can be done very quickly. Right? So now let us believe this. Right? And now let us go back to the Ford-Fulkerson template. Right? You start with GF, you start with a zero flow. you compute GF, you find a path. If the path is there, what can you say about the residual capacity of the path? Can the residual capacity be 0? Is it more than 0? Is it less than 0? What is it? It is greater than 0, not equal to 0. So you have a flow F, you compute the residual network and you take a path in the network. Right? In the network, if an edge has capacity 0, it means the edge is not there. So therefore, if you find an ST path, the capacity of every edge in that path is greater than 0. Therefore, the minimum, which is the residual capacity of that particular path, is greater than 0. So F prime, the value of that particular flow, right, we will argue is also greater than 0. Right? Therefore, when you add the two flows, you will have a strict increase from iteration to iteration. That is, if you started with a flow F, find a ST path in the residual network, its residual capacity will be more than 0, right? And once you implement this particular formula, we will observe that the flow in the network will strictly increase, right? Because I did convince you that the value of this flow is, augmented flow is the value of F plus the value of F prime, right? Therefore, from iteration to iteration, the value of F will be strictly increasing. Fine. So therefore, you will keep finding larger and larger flows by the Ford-Fulkerson template. Right? So therefore, we go to the natural question. When is this going to stop? Is it going to stop at all? Right? Is it bounded? Fine. So therefore, we are going to introduce a few new ideas to argue that. Okay. So therefore, this is essentially the progress of the Ford-Fulkerson template. I call it a template because it only tells you, right, what you should do step by step, right? It doesn't tell you which path to pick, which ST path to pick, and so on and so forth. All those things will control the runtime efficiency of the algorithm. Right? Right. When does the Ford-Fulkerson template stop? In other words, can the value of F keep increasing? So what am I going to show you now? That the value of every flow is upper bounded by some very interesting parameter associated with the given flow network itself. So it cannot cross that limit. I am going to show you that. Right? To do that, I need to define. Right? To answer this question, I need to introduce some new combinatorial and graph theoretic parameters. I am going to define what is called an ST cut. An ST cut is a partition of the vertex set into two parts. One part is called S, the other part is called T. S union T is equal to V. S is present inside the small s, the source is present here and the terminus is present here. Right? And S intersection T is empty. This is what is called an ST cut. Fine. It's just a partition of the vertex set into two parts. One part should contain S and the other part should contain T. Right? We will define something called the capacity of this cut. So obviously there are edges that are going from here to here, right? So therefore, the capacity of, like the capacity of an edge, we are going to extend the definition of the capacity of an edge to the capacity of a cut. Right? You can think of this as every road in the network has a capacity, how much traffic it can carry. Right? Now if you partition a city into two regions, and if you have all the roads going across, the sum total of the capacity of the individual roads is considered to be the capacity of that way of partitioning the city into two regions. This is summation V belonging to S, U belonging to T, the capacity of U comma V. So this is called the capacity of the cut. As you can see, this definition does not have anything to do with the algorithm that we have discussed about the Ford Fulkerson template. Given the flow network, for every cut, this capacity is a well-defined number. Right? I am sure some of you have an intuition, right? Or if you just think about it, you can see that this could be thought of as the resistance, right? If you were observing the network from these 2 points. Some sense this is like the effective resistance, right? So it's just a superficial way of talking. We'll try to formalize this a little later. Right? So now I am also going to define, right, I am going to extend the definition of f. Recall that f is a function which is defined only for pairs of vertices, right? Right. Now I am going to define it for cuts also. I am going to define, and I am going to use the same notation f, right? So in this case, u and v are two vertices, right? uv is an edge and the value of the flow has been given there. I am going to extend the definition of f and I am going to call it f of s comma t. This is going to be, right? Can somebody guess what this is going to be? Okay, it is a sum of the flows from S to T. Is that all, or you want to be? Very good. Exactly, right? So what she says is right. So what you do is you define this as see, remember that you want to keep track, you want to define concepts, right, which ensure that you don't overcount. It has this behavior of a current like behavior, right? So this is f of u comma v minus summation u belonging to S, summation v belonging to T. Can somebody complete this for me? What would I put in here? F of EV, quite obviously. Right? Again, for a flow, I am introducing a new parameter. Right? The intuition is quite clear. Right? So the total amount of current that is going from the set S to the set T, right, is taken by the total current that is going from each pair of vertices, one in U, one in S, one in T. Take the sum total and subtract out the current which is actually flowing in. Right? So that's the effective amount of current that is flowing across from S to T. Fine. Now we are going to observe some parameters. Now, but those parameters you can intuitively tell me.